Hello everybody, welcome back to Arduino for Amateurs. This is episode number 20, I2C real-time clocks. As always, my name is Matt Gracie. I'm a hacker from Buffalo, New York. I'm a member of the Bidhaven Hackerspace. And what I'm going to be talking about in this video is how we add a real-time clock module to our Arduino circuit. A real-time clock module is exactly what it sounds like. It is a hardware timekeeping device that you can put a battery into so it can maintain the proper date and time stamp even when it's turned off for an extended period of time. So if you have a design that you want to do that changes things based on time, maybe you want to have a time or a date readout on an LCD, or maybe you want to set up a lighting project that turns lights on and off or activates sounds at different times, if you want to have some sort of alarm functionality, that's all stuff that you can do with a real-time clock. So much like with the last two videos, we're going to be attaching that real-time clock module using I2C, or Inter-Integrated Circuit. This is, once again, a very simple embedded communications protocol. It's a bus that operates on a controller target paradigm. So your Arduino acts as the controller, as the master. And then there are a bunch of subsidiary devices, targets, each of which has an individual address, and you're able to interact with them over the I2C connection. This is really cool because I2C requires 4 wires, right? Power, ground, clock, and data, and that's it. Every device uses those same 4 wires, so it's really easy to add devices to the bus so long as they have unique addresses. The particular device that we're adding today is one of these. This is a R2C module. Let me just point out a few features here. One, we have these 6 pins along the bottom. So these 4 are the ones that we're going to use. This is our serial clock, our serial data, our voltage in, and our ground pin. Over here, we have a wave generator and a clock signal. Those are used in some hardware designs, but not in anything that we're doing today with the Arduino. So we can ignore those 2 pins. We're only concentrating on these 4. So again, just like every other I2C device, we've got a clock, we've got data, we've got power, we've got ground. You'll see these 4 pins are also replicated up here as through-hole solder points for clock, data, power, and ground. These are electrically identical. You can connect either one of these to your circuit, whatever works better. So if you're soldering this in place, if you have some device that needs a clock that needs to be portable, you can use these through holes and solder in whatever leads you need. If you're using it with a breadboard, which is what we're going to do in this video, you can use these pins and plug it into your breadboard and wire it up that way. Another thing that I want to point out, here we have these A0, A1, A2 solder pads. Those may look familiar. We saw something similar with the LCD backpack, the 1602 backpack in an earlier video. Those are for setting the address of the device on your I2C bus. By default, the RTC has an address of, I think, OX58. We'll see that in a minute with the scanner. But if you need to have multiple devices, if you need to keep track of the time in different areas, or using, different sensors or whatever, then you can jump these together and it will change the internal addresses that are being advertised by your real-time clock. The reverse of the clock, you see here, and it's a little blurry, I apologize, but this is a coin battery. So you can put a 2032 coin battery into this real-time clock unit. And what that will do is it will keep the oscillator going. It will keep the clock going even when the circuit is not being powered. So if you have a real-time clock, it is exactly that, a real-time clock. It will continue ticking along, and then when you turn it back on, it will still have the accurate date and time set on it. One thing that I want to mention, you can use a regular coin battery here, or you can use a lithium rechargeable coin battery. The RTC, when you connect voltage to this VCC pin, can operate on either 3.3 volt or 5 volt input. If you are using a rechargeable, a lithium cell, then you could hook it up to the 5 volt. If you are using a alkaline, a regular non-rechargeable coin battery, you want to hook that up to the 3.3 volt. Because any more than that, and it will activate the charging circuit and attempt to charge your unchargeable battery and could lead to hardware damage or problems, possibly even a fire. I don't know. So just be aware of that. There is a charging circuit on here that you can desolder or you can break. I'm not sure where exactly it is. You can check the documentation for more information on that, but the easiest thing to do is just make sure that you've got the proper variety of coin batteries set up. So if we go down here, there's our coin battery. If we go down here, this is the circuit that we're going to be working with today. You'll notice this looks a lot like the circuit from the last video. All I really did was add the real-time clock here in the middle. So just to go over the connections from before, this is our temperature and humidity sensor. This is our real-time clock. This is our LCD 1602 panel. All three of these are I2C devices, right? So we have a red 5 volt lead coming off of our Arduino here to power the LCD. We have a red 3.3 volt coming off of here to power the power rail on our breadboard. And then we also have a ground wire coming over here to our ground rail on our breadboard. Each of these devices is hooked to these yellow and green wires. The yellow wires are for the serial clock. You can see there's a yellow wire plugged in right here at the end of our Arduino, the serial clock. That is plugged in to this row of tie points, and then we have a yellow wire going over here to the LCD. We have one going over here to the temperature sensor, and we have one going over here to the real-time clock unit. Same thing with the green. The green wire from the serial data pin on the Arduino comes over to this row of tie points, and then you see we have 3 green wires, one going over here to SDA on the real-time clock, one going to SDA on the temperature sensor, and one going to SDA on the LCD backpack. So this is a good illustration of why it's nice to have I2C devices. They're all using the same protocols. They're all using the same wiring scheme. It makes it very simple and clear to hook up these sort of devices all to the same circuit. If we zoom in a little bit, right, we'll see exactly what we were talking about. We've got the yellow clock wire, the green data wire coming over here to this row of tie points, and then our devices wired in line. Each of these are being powered off of this 3.3 volt rail. You can see that here, you can see that here, and they're both being grounded back to this ground rail. So we have 3 I2C devices all connected to the Arduino at the same time via these clock and datas. So let's go to our I2C scanner and make sure that everything is reporting in the way that it's supposed to be. So I've opened up my serial monitor. This is the same scanner sketch that I've used in the last couple of videos. I'm going to upload it so it'll compile a fresh copy, send it out to my circuit, and you'll see here, let me pause the scroll on this. You'll see here I am reporting back with 4 devices. I've got 27, 38, 57, and 68. So 27 and 38, we remember from the last video, those are our temperature sensor and our LCD panel. But these other 2 are new, 57 and 68. So it looks like our real-time clock is giving us 2 addresses. It's responding to 2 different addresses when we probe the I2C bus. And that is correct. That is expected behavior. I was surprised too. But when I looked at the documentation, it turns out that the real-time clock card also has an EEPROM in it. That is, it has a small memory cache in it that is I2C addressable. And the intention is to use that for things like logging data, right? So you have some battery-backed storage on your R2C chip that holds 4K that you can write or read data to. We're not going to do that in this video, but that's kind of an interesting thought that you can cache data in this thing so that it remains even if the circuit's been powered down. And then 68 is the actual clock chip. So that is the real-time clock function that we can query or we can set a time and a date in and then retrieve that later. So we've run our I2C scanner. We know that everything is up and running, everything is powered, everything is responding. Let's take a quick look at some basic R2C code and see how this works. So this is a super simple RTC library sort of demo unit here. You see here we are using the library rtclib.h. I don't think I've installed that on this machine I'm recording with yet, so let's go ahead and install that. rtclib by our friends at Adafruit. We'll install it with all the dependencies. Yes, indeed. Okay, close up the library. So we have installed rtclib 2.1.4. So let's take a look at the code from the top. We've got include wire.h, and we know that's our library for dealing with I2C connections. We have include rtclib.h, that is our real-time clock library. So that's the commands and the drivers and the interface stuff that we need to interact with this real-time clock. The first thing we do is we create a RTC_DS3231 object. So there are different hardware platforms and different chips that are used to provide this real-time clock functionality. This particular one that we're working with today, this is, again, something I got off Amazon. I think it was $7 or $8 for a 3-pack of them. Is based on the 3231 chip, so that's the one that we're using. We're going to call that object RTC, and this will be the object that we interact with in order to set and read time and date values. Our setup, we begin the serial monitor because that's how we're going to be interacting with our real-time clock in this video. If we cannot run rtc.begin, that is, if the clock cannot be initiated, if I cannot touch that hardware component and start it, then it's going to write to the serial monitor, couldn't find RTC. So this is just a quick little hardware check to make sure that my real-time clock is connected and is behaving appropriately. Then we're going to set the real-time clock date and time to the date and time that this sketch was compiled. So what this will do is it will set a initial value. It will seed the value of the date and time from the system time on the computer that I'm compiling this on. And then that will be inserted into the real-time clock, and it will count from there. In our loop, again, this is very simple. We are creating an object of type date time. We're calling it now. And we're seeding that with the value RTC running the function now. So this now function pulls the current date and time from my RTC, from my hardware device, and puts it into this variable called now, which is of type date time. And then the rest of these are just printing to the console. So I print the year in decimal format. That's what this comma DEC is. I print a slash, I print the month, I print a slash, I print the day, and I print a space. So overall, this is going to give me year/month/day. And then it's going to give me the hour, the minute, and the second interspersed with colons. And then it's going to give me a line return. It'll delay for 3 seconds, for 3,000 milliseconds, and then go back to the top of the loop, pull that data again, format it, print it to my monitor, right? So I'm going to turn on the serial monitor. Okay, I will clear this out because that device is, program is still running. Okay, clear that. And we see here, I've got 2026, April 19th at 20:43. And it is refreshing the screen every 3 seconds, which is exactly what I would expect from this delay 3000, right? If I run this again, if I upload it again, it compiles, and you'll see it keeps counting. 49, 52, 55, etc., right? 3 seconds at a time. Now, one weakness that I want to point out is, as you see in the setup function here, it sets it to the date and time that the sketch is compiled, not the time that it's uploaded. So this is 2043:49. If I unplug this from the power, Okay, you see not connected. I've just unplugged the Arduino, and then I plug it back in. You see it goes back to 4349, 4352, 4355, right? So in order to refresh that initial seed value, I need to recompile and reload the firmware on the Arduino. That's why that coin battery is so helpful, because if I put a coin battery into this RTC unit, then if I unplug it, unpower it, the clock will continue to advance. And then when I plug it back in, it will have the right value in it, right? It won't need this code to be recompiled and pushed in there again. All right, so that's what the RTC does. It's a hardware device that stores the date and time. I seed it initially, and then I'm able to count from that point and stay precise. So let's combine this with our little LCD 1602 panel from before and see what this looks like going together. So we'll go back here. And what I've done is I took that temperature sensor desk clock code from last time, and I folded in the RTC code that we were just looking at. So it's getting a little more complicated, but not much. So we'll start here, right? We'll start at the top. We have wire.h, that is our generic I2C library. We need that for interacting with all of these devices. We have the Adafruit AHTXO.h. That is the library for the temperature and humidity sensor. We have the liquid crystal underscore I2C.h. That is the library for the LCD 1602 with the I2C backpack on it. And we have the include RTClib.h. That is the library for the real-time clock. So these are the drivers and functions and headers and so on that we need for all of the pieces in that circuit. So in this circuit that we've got here, we've got our display over here, we've got our real-time clock here, we've got our temperature sensor here. These are all wired together, and they're all using those different headers to give us a programming interface into these pieces of hardware. Our setup, we begin the serial monitor. Now the serial monitor is not going to be our primary means of interfacing, but it's still helpful for stuff like debugging messages. And we say AHT20 sensor test. If AHT20 can't begin, that is if the temperature sensor can't be found or can't be initialized, print an error message, could not find AHT20. Same thing for the RTC. If the RTC.begin fails, then we print couldn't find RTC. Right, and leave that alone. So this is sort of a built-in test to make sure that we've got these components wired up properly and they're going to behave the way we expect them to. Once we get through these, then we're assuming that these devices are responding, and we say, okay, well, I'm going to set RTC to the date and time. I'm going to print a message to my serial console that says, I found the humidity sensor, I found the temperature sensor, I found the real-time clock. And then I'm going to turn on my LCD, run lcd.init, run lcd.backlight. So these are my setup commands, right? I'm probing and checking and turning on all of the hardware in my circuit, making sure everything responds the way I expect it to. Once all of that is done, now I can move on to my loop. So what my loop is going to do is it's going to first pull a fresh humidity and temperature reading from my AHT20. It is then going to create that date time object we call now with rtc.now. Then it's going to put the cursor on the first row in the third column of our display. And the reason for that is purely aesthetic. It's so things line up, and I'll show you that in a moment. And then it's going to print the month / the day, space the hour, :minute, :second from our real-time clock. And then in the next line, it's going to move the cursor to column 0, row 1. So the second row, again, we start counting at 0. And then it's going to print temperature in Fahrenheit and then the temperature converted to Fahrenheit, because my American brain remembers Fahrenheit and comprehends Fahrenheit values better than the Celsius values that this natively generates. So what I should have after I run this is a nice little display I can leave on my desk that'll print the current date, the current time, and the current temperature in my office. Then it will wait 2 seconds, 2000 milliseconds, and then go back to the beginning here. Draw a fresh reading, pull the real-time clock value again, and update the display. Now, unfortunately, as we've seen in a couple of these videos, if I just hold the screen up in front of the webcam, it's not going to work so well. So I ran this earlier when I was working out all this code, and this is what it ends up looking like, right? Exactly what I was talking about. April 19th, about 2:28:53 in the PM. Temperature was 68 degrees in my office, which is nice. I mean, it's April in Buffalo and it was hailing, so I'm glad it was at least fairly warm in my office. So if we have a temperature sensor and a real-time clock and an Arduino and an LCD, we can build this 3D printed enclosure and have a wonderful simulation of the experience of driving past a bank and getting the time and date and temperature. Pretty cool. So I think for my next video, I'm going to do some more stuff with the real-time clock. I'm not quite sure what yet, but stay tuned and we'll figure it out together. Thanks.